Suppose a bank has a vault and that the vault can only be opened with some secret password S. Now the bank has 4 tellers, let's call them P1, P2, P3, and P4. And we do not want to give the full password to any one teller, because then that person could open the vault alone, let's say. Instead, we would like to distribute the secret among the tellers in a smarter way. So the goal is that any 3 tellers can work together and recover the secret. So if any 3 of them get together, they can get the secret password and then open the vault. But any 2 or fewer tellers should learn nothing about the secret at all. And so this learning nothing about the secret, this is stronger than, for example, just splitting the secret password into pieces. If 2 people get together, they should not just know part of the password. We want them to learn nothing about the password. So they should learn no information about it at all. Okay, so how can we do this, right? How can this be done? And so Shamir had a nice way of looking at this problem. And the idea is to hide the secret inside of a polynomial. So in this example, we want any 3 tellers to be able to recover the secret. And so we choose a random polynomial of degree 2, because a degree 2 polynomial is determined by 3 points. So if you have 3 points, that determines a parabola. And if you have, let's say, so here, for example, if we set this parabola to be the parabola that's related to our secret, and we give points to the different tellers, if 3 of them get together, they can determine the parabola. But if only 2 of them get together, one can show that then you get too many parabolas that can pass through here and go over all the different values. Now this, of course, is a visualization. We're going to talk about this more formally later on, but this is the idea behind the scheme. So how does this work? So let's make this concrete. Let's say that our secret is an element of Z5, and later we're gonna see why we want to be working over integers modulo something. Well, I mean, actually we'll see right now in the next line, but the point is you can work over, if the secret is larger, just work over a larger size here of the set and so on. But just for illustration so just for illustration purposes, let's keep it small and simple. So let's work in Z5. And so the idea, like we said, is to generate a random degree 2 polynomial. So how do we do that? We have our secret, and then R1 and R2, we are going to generate them at random from Z5. So remember that Z5 is the set with the numbers 0, 1, 2, 3, and 4, where we do clock arithmetic, right? You put the numbers around the clock, and you do the arithmetic around the clock. So we choose R1 and R2 from this set here, uniform at random. That means there's 1/5 the chance of selecting each one of these, and that will generate our random polynomial. And then the idea is that we're going to give an evaluation of this polynomial, so distinct points, to each one of these tellers, right? And so teller 1 is going to get f of 1, teller 2 f of 2, teller 3 f of 3, teller 4 f of 4. And the idea here is, well, f of 1 is the secret plus some random stuff. F of 2 is the secret plus another combination of random stuff, and you have different combinations. Now, if you combine any 3 of them, you can check that you have 3 equations. So you will know this equation, and this equation. and you have 3 unknowns, so you can solve for each of the equations and retrieve your secret. But if you have only 2 of them, it can be shown that they're not able to get rid of this random stuff. So they're not able to sort of decode the randomness, and they learn nothing about the secret at all, right? So yeah, and so this is called a 3-4 threshold. So it's a threshold scheme because it means that 3 or more participants can decode and less learn nothing, and we have a total of 4 participants.